the DP1 stuff good, thank you. We're going to be introducing, yeah, the stuff that's specific to DP1, and this is sort of interesting timing. I don't know if this was emphasized before, but like, DP1 is almost sort of a bit old now. We're very close to getting Data Preview 2, but there's still lots of valuable things to look at in DP1. But if you stay for later on today, you'll find out more about DP2 specifically, and yeah, the prompt products and alerts that also have solar system data. Um, and yeah, you've probably seen this slide plenty of times, but just to emphasize again that like if you have any issues working with Data Preview 1 or any other Rubin data or anything else to do with the Rubin Observatory in general, like the community forum is really one of the best places that you can go to get some help. Like even before I got more formally involved with Rubin, this would be where I would go all the time, and it's sort of this one of these things where it's like, oh, I'm worried about asking a stupid question. There's really no stupid questions, and I've personally found this to be a really good resource because if you have your question, you can search through, see if someone might have already asked the question that you're interested in getting the answer to. And even if you're the one to ask the question, then your question is there for another person to help to be helped by. It's this general, it's an ever growing resource of tools, and everyone's very friendly, and lots of people can chime in and offer advice. So great place to get some advice. And yes, so the focus of this talk, as I said before, is Data Preview 1. So pretty much everything that we're going to be covering in today's session is available at this documentation site, dp1.lsst.io. The little asterisk here is just to highlight that towards the end of this presentation, we'll also cover some additional solar system data that is currently publicly available, but not necessarily fully packaged up with DP1. There's some stuff that's available at the MPC, which is the Minor Planet Center, which we'll explain later. And as I said, DP1 is sort of old data at this stage. DP1, as you probably heard in the earlier sessions this week, comes from ComCam, the commissioning camera. So this is only a small sort of subset of detectors compared to the full 189 detector field of view that the full LSST camera, which is now in the telescope, has been working on. And the actual data itself for DP1 was taken in October to December 2024. And yes, you can get a full overview of DP1 at the review paper here. And yeah, there's lots of information that you're able to go to. I generally go to this .io link to start with because it lays things out really nicely. But here's what you need whenever you're citing things. And yes, we'll be focusing on the actual catalogs that are available in DP1 relevant to solar system objects. So in this session today, we're going to go over, first of all, the data processing, how the solar system data was extracted from the DP1 images. So that involves what happens in the difference image analysis, how moving objects are linked and detected and verified. Then we'll get an overview of the data products. So as you're probably aware, Data Preview 1, there's catalogs. The main catalogs that we're interested in for solar system science is DIA Source, Solar System Source, Solar System Object, and MPC Orb. Orbit tables will cover what's in those and why they're important. And then we'll go through a couple of brief tutorials using the Rubin Science platform, once using the portal aspect to sort of have hands-on look at the data. And then we'll go to the notebook aspect of the Rubin Science platform and look at one of the tutorials there. And then, as I mentioned, we'll briefly end with information about this additional photometric data that's available sort of outside DP1, but quite complementary, being that it's the some good publicly available data that you can work with right now before the main survey actually begins. And so it's important to understand the sort of key concepts with how this data preview one and the solar system data was brought together. Um, so because we're doing difference imaging in this survey, we need to have template COAD images for the regions of the sky for which we want to generate alerts. So in this case, we're defining a template COAD image is the combination of previous good quality visit images that have been co-added and combined to provide a map of the static background sky. So whenever the pipeline runs on a new visit image, the pipeline does this image subtraction. So that static sky template is subtracted from the visit image, creating a difference image which only contains sources that weren't in the original static template background. And this process overall is DIA, difference image analysis. That will be used as shorthand throughout. And then in terms of the sources that are detected in each of these visit images, specifically difference image analysis source, DIA source, that's any detection made in that new visit image that is greater, a signal to noise ratio greater than 5. Noting that that is in this difference image flux space. It's not like a sky visit image flux space, it's in the difference image flux. And then specifically SS source, that stands for solar system source, signal to noise ratio greater than 5, moving object detection in a single difference image. So this is where solar system starts to become a bit more specific than the wider DP1 catalog. The DP1 contains many, many, many DIA sources for each of the visit images, but only a subset of those DIA sources will be a corresponding SS source. It's a DIA source that's been matched with a moving solar system object. So that's what makes it specific to solar system. And then yes, as I mentioned, these are solar system objects are moving objects, so that's why they appear in these difference images, is because one night the asteroid might be in the field of view, the next night it's moved on to a different position in the sky because the asteroids and comets are moving on their orbits. So in order to turn these DIA sources into SS sources with a matched orbit, the solar system processing pipeline will construct tracklets. So tracklets are 2 or more detections of an object on a single night in different visit images. Because the general survey strategy will be that LSST will revisit each patch of the sky twice in one night. So that gives you up to maybe 60, 90 minutes time difference. Depends on the actual survey strategy of the night, but that's enough time for an asteroid to have moved from slightly away from its previous position. So the pipeline will try and find these sources that have moved slightly between these pairs of images and turn them into tracklets, and then its tracklets are then linked across multiple nights to define a moving object, but we'll talk about that a bit later. And then you may have noticed in the other general DP1 discussions about catalogs, there's a difference between sources and objects. So within LSST language, an object is generally sort of a grouping of sources for whatever reason. So, for example, most objects will probably be a DIA object. This is a static object that, like a variable star that has been detected in one part of the sky and has a collection of DIA source detections associated with it. Correspondingly, the solar system has SS object. So this is effectively like the asteroid name in the LSST catalog, but it's the group of DIA sources that are associated with this one object moving on its orbit through the sky that have been linked. And then this is quite a busy slide showing how this general solar system processing works. Sorry, I think I need to dismiss that. Hopefully you can see that okay. But this is like trying to summarize the sort of linking and loop that's occurring whenever solar system processing is happening. The main takeaways from this is that first of all, the telescope takes an image, the pipeline does the difference image analysis and finds the dia sources in that image. Then this linking of tracklets occurs, and these tracklets are built up over time until the pipeline determines that, like, okay, I've got multiple tracklets of a candidate object on multiple nights. Once the pipeline has a sufficient number of tracklets to have a reasonable confidence that this is a single moving object, these discoveries can be submitted to the Minor Planet Center, the MPC. This is the sort of external body to the survey that handles the observations and discoveries of new minor planets, asteroids, and comets. But then the important thing to note is that then the pipeline ingests an updated MPC orb, Minor Planet Center orbit catalog, that is produced by MPC. So this is where that loop connects back. So the pipeline has submitted discoveries. Discoveries are managed by the Minor Planet Center, and then the pipeline updates its known objects list with this new catalog. And by doing that loop, that means that the pipeline has knowledge of which objects are known, so that they're able to associate any new dia sources with known objects by using the predicted positions of those known objects. And that's how that loop goes around and round. And then just a bit more detail on that actual making of the tracklets and orbit fitting. So as I said, the things that are unmatched dia sources that don't have an associated moving object, they can then be used to make a whole number of candidate tracklets. And remember, a tracklet is made up of a single night's worth of detections. So it's just a small portion of the orbital motion of that object. But then these candidate tracklets are passed to this software package called HelioLink. And what HelioLink does is it tries and takes these small snippets, these tracklets on different nights, and links them into longer tracks. So that's what I was mentioning before, is that the pipeline will only submit things to the Minor Planet Center that they're reasonably confident is a moving object. So to do that, you need to be able to make a longer track that's made up of at least 3 component tracklets. So given the way the survey strategy works, an object will generally only really be submitted after approximately 2 weeks of observations, just given the nature of how frequently the survey is expected to revisit that particular moving object. And yeah, as I said before, those tracklets are submitted to the Minor Planet Center. The Minor Planet Center does their processing, assigns temporary designations to objects, and then that loop continues back as we described before. And I think this slide just summarizes again what we were talking about in those previous infographics. But the one of the things to maybe emphasize is, yeah, if you go to this DP1 documentation website, it gives you more precise details about exactly how this was implemented in DP1 specifically. Because one of the things to be sort of considered is, obviously, DP1 is early data. There's been various adaptations and improvements made as the process of making this work as like a nice clean loop has been continuing on. And I think the only thing I want to emphasize out of this is that because of that nature of improvements and refinements being made, not all of the detections that were used to define the orbits are necessarily available in the final Data Preview 1 release due to like image quality issues or problems with those particular dia sources. So, for example, an object might have had 20 dia sources submitted to the Minor Planet Center to find the orbit, but then only maybe 10 or so maybe could have made it through to the actual this is in the DP1 catalog, because maybe some sources were had issues with their detection and stuff. Not a huge problem, but just something to be aware of if you're trying to match up the different catalogs. And yeah, so now we'll go through the different tables that are relevant to solar system science in the DP1, the whole DP1 database. So the first one to consider, of course, is the data source table. If you've been looking at any other science results, science cases in DP1, you've probably already come across the data source table, because this is big. This contains all detections in the data preview 1 campaign. As with all these tables, best way to access them is probably the table access protocol for handling catalog-like queries, but there is also the butler. You can access individual data sources via these attributes. The DP1 release has 87 different columns and like 3 million rows, so it's a relatively big, chunky table. But the important ones to consider for solar system science is, as usual, data source ID. Less important is the data object ID. Instead, what we'd want to focus on is this thing that you might not have come across before, SS object ID. So this is this way of associating a given data source with a known solar system object. There's the general visit info, so probably most importantly here would be the band you're observing in and the time of the observation. RA and DEC, again, this is going to be more important for solar system science than static transient science, because these sources are moving across the sky, so the RA and DEC is changing for data source ID for a given SS object ID. And then, the brightnesses come in fluxes. The best ones to use for solar system science, PSF flux and science flux. And I should point out that you can access more details of these schema at SDM schemas, or the portal's user interface, which we'll look at later. Now, the next table is the solar system source table. This is specific to solar system sources. So as you can see, there's much fewer rows. These are all the detections of solar system objects in DP1, so it's a subset of that larger data source table. But again, it's got a corresponding data source ID to allow you to match it to data source. It's got a corresponding SS object ID, so you know, again, which object is the sort of parent object of these detections. And then the reason why the SS source table exists is because it contains a bunch of additional information associated with the data source that you would want for doing solar system science. So from the orbit information, the heliocentric distance, topocentric distance, phase angles, and velocities, those are all provided to enable you to do actual solar system science with that detection. And then onto the SS object table. So as we described before, static sources, the corresponding object table would be data object, but we're solar system, so we need a specific solar system object table. You can see that this has 431 rows. This is the number of objects, solar system objects that are available in DP1. This is quite a sparse table. It's only got 3 columns. This is obviously going to be bigger in the subsequent data releases, but it gives you just the basic overall overarching information about individual solar system objects in DP1, namely the number of observations and the discovery submission date. So we'll find out later in the tutorial how this discovery submission date can be used to separate previously known solar system objects that were detected in DP1 to new discoveries that were made as a part of DP1. And then also on this sort of object level is MPC orb, minor planet center orbits. Again, the main index is SS object ID, so each row here contains information about all known solar system objects. So it's got their orbits, perihelion, eccentricity, inclination, estimate of their absolute magnitude. And note that this is much bigger than SS object, but that's because this is part of that data loop. MPC orb is downloaded from the Minor Planet Center as part of the pipeline. So this is, the 1.5 million known solar system objects that have well-defined orbits in the Minor Planet Center. So we access this to match up on SS object ID, and then we can do orbital analysis, which we'll look at a little bit in the tutorial as well. So speaking of the tutorial, we will switch over to the portal in a moment. But as I'm sure you've been made aware in the other demonstrations throughout the week, sort of ADQL is one of the main ways to interact with these catalogs and data. Similar to SQL if you've used that before, but basically you construct these queries where you are telling the service, I want to select, Q for perihelion, E for eccentricity. They come from MPC, which is in this case the MPC orb table, but especially with solar system objects, as you saw from like the 4 main catalogs that we're using, you will probably have to join catalogs together to get all your data together. So in this example query that we're going to look at, we're joining MPC orb to SS object in order to look at the orbital parameters of this data. So I will just select this while I'm on it. And now we'll go over to the RSP. So hopefully you all already have RSP accounts, but to get to the RSP, data.lsst.cloud, that gets you to this landing page here. You'll need to log in. So this should be a simple process once you've got your account. I need to verify my ID. In this case, I use OrcID. There we go. I'm logged in as JRob. So first of all, we're going to look at the portal user interface, which is sort of a more hands-on way of interacting with the data. So we're on the portal here. Hopefully that's big enough. Whenever we're going through this, we can see up at the top we have a number of different sort of data sets that are available. In this case, we want to get the actual row by row catalog data. You can also go and request images and stuff from the DP1 images, but we'll go here, DP1 catalogs. And what you get in this overview is, we're in DP1. In this drop-down menu here from tables, we can then take a look at all the different tables that are part of DP1. So the object table, right now, we're not super interested in that for solar system science because that's focused on static objects. What we're probably more interested in is something like data source, because even though data source contains static objects, the subset of that will be solar system objects. And what we can do is we can take a look at get an overview of the schema here in this table. So we have all the different columns that are available. In this case, we're quite interested in SS object ID of the SS object this source was associated with. So we can get some overview information about what's actually in this table. But like I said, we can also go to SDM-schemas. And this has lots of different data sets, but if we go to data preview 1, we can also get another view of what's in these different tables. I find this webpage quite useful for being able to search around and try and remember which table things are in. But then on the left here, when you're interacting with this data, you can, there's lots and lots of rows in data source, so we probably want to filter things down. So you can enter spatial constraints, temporal constraints, or search on a given ID. That could be like data object ID or data source ID. But in this case, because we're wanting to do a slightly more complicated operation, we can go down to this button here where we can directly input an ADQL query. Oh, sorry. You have to unselect stuff here before you can go into here. But yes, once we're here, we have access to the actual underlying queries that we can put in. So we're putting in this query from the example in the slides. And again, what this is doing is joining MPC orb to SS object, and we're basically retrieving the orbital information and the discovery submission date. So once we put that in here, we can do search to run the query. It'll run away. This should be pretty quick because DP1's quite small. But here we are on the results. So the results are quite handy because they give you a summary plot view. So in this case, it's plotted Q, which is perihelion distance, the closest distance to the sun in the orbit, versus E, which is eccentricity. And we can see the actual rows of data that have been retrieved. So yeah, values for your different orbital elements, but importantly, yeah, we also have the SS object ID, which is sort of Rubin's identifier for a given moving object. We also have the MPC designation, which is the sort of more traditional license plate that you might be more familiar with from interacting with solar system data. But this is cool because it gives you a hands-on way of looking at the actual data. So, you can zoom in using these different tools, for example, to like highlight different bits of the data. So I've zoomed in on this chunk here. If I want to find this particular object, if I click on it, it's highlighted then in the plot. So it's quite a handy way of selecting and finding different things. You can also filter from the plot directly, which is this button here. So if I just want to get these what look like outliers here, I think I can filter like so and just get those. Cool. But let's remove the filters. One of the things, if you're familiar with plots of the main asteroid belt, you might notice that this doesn't quite look like your standard main belt distribution with the different Jupiter resonances in it, and that's because we're plotting the perihelion distance. So what we might actually want to plot instead on the x-axis would be semi-major axis. So semi-major axis, it's not provided directly in the table just because it can be easily calculated from the perihelion and the eccentricity. So if we apply that and take a look, we have something that looks more like the main asteroid belt. Like so, you've got your Jupiter resonances opening up the gaps in between. And yes, what you can do is you can do a similar operation as well by adding a new column. So we could add a semi-major axis. So we could add a new column to our data, and then likewise you could go in and change what's being plotted to be that directly. So yeah, the portal is a really good way for highlighting this. And then one of the things else that we might want to do is show only a subset of the data. So we can also filter from here. And I mentioned previously there's this discovery submission date, so you'll see that it's blank for most things that were previously known objects. You can see that their license plate all have years that are previous, old enough that these were obviously known objects. But what we could do is filter this, because anything that was discovered by Rubin will have a discovery submission date associated with it. So by adding this constraint, give me the discovery submission date greater than 0, it returns only the subset of objects that were actually discovered as part of data preview 1. And yeah, you'll see that correspondingly all of the minor planet center designations have 2024 in the name. That means that these were objects discovered in 2024 when DP1 was running. So that covers a very quick overview of the portal. What we'll look at very quickly next is some of the tutorial notebooks. So this slide here shows a list of sort of the most important tutorials that you would want to be going through as part of understanding solar system objects in DP1. If we go to the main DP1 documentation page, we can see these tutorials actually rendered, and you can just go through them as a web page. I personally have found this really helpful using the search function here to try and find, specific things about like SS object, or more specific bits. But it's a really handy way of, parsing this data rather than digging through lots of different notebooks. But what we'll do now is show quickly the notebook aspect of the RSP. So we've gone back to data.lsst.cloud. I'm already logged in. I'm going to go to the notebook side of things rather than the portal. So the notebooks obviously allow you to then do the same sort of things as in the portal, but in a much more programmatic way. Generally, this is quite handy for, if you want to do a more detailed analysis using DP1 or any other Rubin data. But you arrive here, you have your landing page. Let me zoom in a bit. But to get to the different tutorials that are available, you can use this drop-down menu. And the way this menu is laid out is really handy to see what you actually need to go. So we want to go to DP1, and then you'll see that then there's 100 series, 200 series, 300 series. So this is sort of 100 is the most basic overview, 200 details the actual data products. In this case, we might be interested in like the various catalogs, such as SS object. And then 300 is the actual sort of, let's use these for science now. So we want to go to 300, 308 for solar system, and let's look at the orbits again. And you'll see I already have this open, so it'll prompt me to overwrite because I've already run this before. But yes, basically we can now go through this tutorial running it as a notebook, so executing each cell. So as usual, we have to import some basic packages for plotting and working with data, but importantly, we import lsst.rsp to initialize the tap service. This is the way that we're going to be able to interact and query with the DP1 catalogs via tap. So we set up the service, check that it exists well. These other cells are just setting up some plotting functions. Then here we define a specific function because we're going to be looking at the orbits, again, similar to how we looked at it in the portal. But this function here is set up to define the different dynamical classes that... I'll just overwrite that and start again just to make sure. I'll restart my kernel as well to be extra safe. Well, hopefully that works. Well, luckily I've already run most of the notebooks, so I'll just run through it as is. But yeah, sorry, this function is just defining the different boundaries in dynamical phase space to set up different groups, such as like Apollo asteroids, Centaurs, MBA is main belt asteroids. And then we're gathering the data, we're running the same query that we ran on the portal, but we're doing this by submitting that query to the service. You've probably come across similar tutorials throughout the week, so I'll just sort of keep going. But basically, we should get data from this back saying, we have 431 unique objects and we have the orbits from them in DP1. As I said before, we can add these constraints, such as discovery submission date. So the 93 objects that are newly discovered by Rubin as part of DP1, we access that by querying discovery submission date greater than 0. And then this is where the value of going to the notebook comes in, is because you can make much more detailed plots than you can with the portal interface. The portal interface is great for that quick first look, but then I would go to the notebook to make a more detailed plot. So I'll skip through that code, but basically we get these summary plots similar to what we had before. So semi-major axis against, in this case, eccentricity. And it's been color-coded by that dynamical classification that was defined further up. So you can see in pink here the majority of the objects are the main belt asteroids. Up here are near Earth objects, so these are on objects that orbits are eccentric enough to approach near the orbit of the Earth. So there's a small number of those and various other subsets of the dynamical classes. So that's showing all 431 objects on the left. And then on the right, there's the subset 93 of objects that were discovered by Rubin itself. And then, yes, good practice in your notebooks is to clean up some memory by deleting your different results in space. So I'll go back to the slides now. As I said, yeah, this is the list of the various notebooks that you want to really focus on if you want to get caught up with Solar System objects in DP1 across the 200 and 300 series. And yes, so in the last couple of minutes before leaving some time for questions, I alluded to before that there's this sort of not quite DP1 but additional set of data that you can use directly from the Minor Planet Center. And that sort of comes about, the best way to describe that is you may remember that some of the first images that you might have seen coming from the Rubin Observatory were released last year as part of this Rubin First Look press release. And, you know, some beautiful images, lots of different things going on there. You may have even seen this beautiful video of, like, asteroids moving across the field of view. But the cool thing about that is that, yes, although, well, confusingly, Rubin First Look was released publicly first, but it contains data that was more recent than DP1, even though DP1 was released after. But the cool thing about the First Look asteroid detections is that as part of testing out the solar system pipelines, those detections in the Rubin First Look images were able to be submitted directly to the Minor Planet Center. And because Minor Planet Center data is publicly available, that means that we do actually have access to these catalogs of asteroids that were detected in the First Look images. So the Minor Planet Center doesn't hold images, but it does hold, you know, RA, DEC, and a magnitude that was submitted. So although it's limited compared to the full detail that you can get with Data Preview 1 and what we would expect with the other Rubin catalogs, it's really, really valuable. As has been shown by, there's already a publication by, for example, Sarah Greenstreet et al. She's in this call right now, looking at asteroid light curves within this. Can skip straight to the cool figure. You know, there's some cool asteroid science that you can do with this multi-waveband, relatively dense light curve coverage. So that's fun. And the way that this can be accessed, there's some links here that give some advice, including there's a tutorial detailing exactly how to do this on the RSP, for example, via querying the Minor Planet Center directly. I won't go into too much detail on that due to interested time, but, you know, it's sort of under this wider prompt products umbrella as well. But I will show this website here that's distributed by the B612 Foundation. So this is a webpage that you can go to, and they're basically curating a subset of the full Minor Planet Center observations database, but just for the Rubin observations. So Rubin Observatory has the EXO5 observatory code. So all of these observations are from EXO5. What you can do is you can download this full set of detections. And I mentioned that, yes, the Rubin First Look detections were submitted to the Minor Planet Center, but since then, as continuing the solar system processing commissioning, there have been actually quite regular bulk submissions of Rubin observations to the Minor Planet Center for observing. So you can get a sense of that from these different partitions. You can see the different chunks of data that have been submitted and the time range that they are relevant for. So if you go to this link, you get the full everything that's been submitted to Rubin. So given that DP1 has a lot of detail, but is actually a very small data set, it's only 431 objects. If you are looking to do more solar system science while waiting for the survey to fully start and data preview 2 to come out, I highly recommend you take a look at this if you're interested in the photometric aspect of things. And I think the last thing that I want to briefly mention that's not in this slide is there are solar system objects in the alert stream. But again, I won't go into detail on that due to interest of time. And I think there's talks later today that sort of cover that more in the aspect of prompt products. And yeah, sorry, there's what's new in DP2 is the next talk today. So yes, we'll find out what we can expect has changed, and how much more data we will get in this shortly coming DP2 compared to DP1, which we've just been discussing. And then later on today again, prompt products, which we'll talk more about alerts. And again, I emphasize that there are currently solar system objects in the alerts. There's another little research note that was out recently from Jake Kurlander et al. Using the alert stream to analyze another asteroid light curve. Thought that was really neat. But I think I will finish there with a reminder to please fill out the exit survey. I'm sure you can find the link in the chat, or these slides will be available. But with that, any questions? Okay, so I see a question in the chat from James Ray. Feel free to unmute, or I can read it out. So the question is there a reason why the SS object IDs are so long, given we don't know of tens of quadrillions of SS objects, and likely won't even by the end of LSST? I'm not 100% sure, but I assume that the length of these IDs are just generally to ensure that you will always have a unique ID. And maybe just speaking from my experience working with this data set, word of warning, because those SS object IDs can be so long. Let's see if we have any. I can't get it right now, but it's they're so long that you do need to make sure that you're always working with them as like either a string or an integer. Because I've accidentally made some foolish mistakes with my analysis where I've accidentally turned SS object ID into a float, which then when it gets turned back to an integer can sometimes get rounding errors and give me a different object. So that's very annoying. So yes, sorry to not answer fully. Maybe does Melissa or Sarah have a better answer? Or
I think your answer was right.
okay, good. Any other questions or things that I alluded to? Like in terms of I had a quick look through the upcoming slides. So I don't think solar system objects are mentioned explicitly in alerts for the prompt products talk, but yeah, I just wanted to highlight that they are definitely there and available. And of course, as the survey fully starts and more templates are built across the sky, we can expect to get larger numbers of nightly solar system objects being detected in the alert stream, which will be really cool for doing rapid science. Oh, I think I see something in the thread from A Juiced. I had a look at the article just now and noted you managed to convert to magnitude. Were these difference images to, and if so, what offset or method was employed? So yeah, by default, Ruben provides all of its brightnesses in flux. Um, Sort of the main reason for this is that in difference image analysis, in particular, because there's subtraction going on, you could get negative fluxes as well, and then that doesn't really work well for a magnitude. So there's plenty of notebooks, examples in the tutorial notebooks about how to convert flux to mag. So yeah, typically when you're doing an asteroid light curve, you'll look at the magnitudes instead. Um, in terms of which, I don't know off the top of my head if it was the difference image flux or the visit image flux that was used in the article. If it was Sarah's article, maybe she can answer briefly or.
Yeah, I can jump in here for a second. So the light curves that have magnitudes in them, as Jamie said, Rubin produces all of its brightnesses in fluxes instead of magnitudes. In this case, this was all data that got submitted by Rubin to the Minor Planet Center, and the Minor Planet Center publishes all of their brightnesses in magnitudes. So this article is all using public data that was submitted by Rubin to the Minor Planet Center and then is made public to everyone through the Minor Planet Center. So this was not using, even though this is LSST CAM data, which is different than DP1 that's LSST COMCAM, it's all data that has been fully public to everyone through the Minor Planet Center. And so that's where we got this data that we then used to publish these light curves and everything. So this didn't come from any kind of proprietary uh, data that would have violated any kind of data policy or anything like that. And the reason that they're magnitudes is because, again, the Minor Planet Center publishes the magnitudes and not the fluxes like Rubin does. So it's a little bit of uh, an unusual situation, or different, at least in the difference between what the Minor Planet Center makes available when Rubin submits something versus what's actually available in the data previews from Rubin itself. Hopefully that provides some clarification.
And I think you touched on it, Sarah. There was a follow up to that. Is it permissible to publish the light curves under the data policy? So, again, as Sarah said, anything that's in the Minor Planet Center is just fully public data. And then I think this will be emphasized more in the prompt products talk later today. But I think anything in prompt products that would be like the alert stream, for example, that's world public data. You would access that through an alert broker, and yeah, you should be able to get that. And then, sorry, I see you quickly followed. Was okay, thank you. But generally, may we publish light curves or not at all, or only when it is folded, or how can we make use of this without contravening the policy? Well, yeah, I guess your question's addressing like use cases for the data in a way. So yeah, the solar system pipeline by default doesn't do a rotational period analysis like this or like this in the alert stream. So if you're finding a new interesting, in this case these were some very fast rotating objects, so there's scientific interest in working with the Rubin data and publishing the result. I hope that answers the question. I'm aware we're probably into break time now, Melissa.
Yeah, that's true. It is into break time, but I think so. A common question that we get asked about the data policy is like, can I show the light curve in a paper? Can I show an image stamp in a paper? Because the data policy is like, you can't share the data, but you have to be able to put the light curve in a paper. So if that's what you meant by like publish a light curve, yes, you can show the light curve in the paper. You have to be able to do that in order to publish a paper. So with data rights, you can show little image stamps in your paper. You can publish papers that have light curves in them, that's all good. Was that the nature like of the questions? Like what can I put in my paper? Yeah, okay. Yeah, okay, excellent. Jamie, I think you got all the questions. Thanks so much for
Okay,
presenting
good.
this morning. Yeah.
Yeah, and as we said at the start, if there's any follow-up questions or other things you come across, Ruben Community Forum, top place to ask.